Welcome. This is the course on stochastic processes and the theory of queues. In this lecture, we will look at the renewal reward process. We have already looked at the basics of renewal process, and we will try to add certain quantification to the renewal process, which makes it more amenable for it to model some real world situations. So, here we have a large number of probabilistic models wherein whenever a renewal cycles happen, as a part of it we get some benefit, or we will call it as a reward. Sometimes it can be viewed as a cost, sometimes it can be viewed as a penalty, and that is depending upon the perception. But there is a related random variable associated with the basic random variables that are the which govern the renewals. So, these two are interrelated. We would like to model these situations, and that is where the renewal reward process comes in. Let us consider a renewal process n of t, t greater than or equal to 0. So, the inter arrival times or the duration between two renewals, that they are all IID random variables. Let xn n greater than or equal to 1 denote the duration between two renewals. We will call it as a renewal cycle. So, the successive renewal cycles are all IID random variables x1, x2, x3 and so on. Suppose each time a renewal occurs, we receive a reward. So, reward is a very generalized term. As I mentioned, it can be a cost, it can be some performance benefit that we get out of a system, and so on. So, we will look at certain examples where it becomes more clear that what we will usually associate a reward to be. So, we denote, so every time a renewal occurs, there is a reward. So, again the reward is not a fixed one, we will let it to be a random variable. So, in the nth renewal cycle, at the end of the nth renewal cycle, we get a reward which we will call it as Rn. So, R1, R2, R3 are the successive rewards that we get in the renewal cycle 1, renewal cycle 2 and so on. So, we have two processes, xn n greater than or equal to 1, which are the duration of these renewal cycles. Rn n greater than or equal to C1 or the sequence of rewards that we get. So, we assume that Rn n greater than or equal to 1, that is the rewards, are independent and identically distributed, but we may let Rn to be dependent upon xn. So, R1 is R2, R3 are such that R1, R2, R3 do not dictate the value of R4. So, they are identical in that sense, but Rn may depend upon xn. Okay. So, this is how we model. The reason, for example, you may be using a machine in a production process. Every time a machine repairs, and if it is immediately repaired, let us say, and then put into one, so the duration between two repair instances is the renewal cycle, and the amount of the production that happens and thereby the monetary benefit that we get or the rewards at the end of the machine breaks down. You look at in that working duration how much of financial benefit the machine has brought in, and so on. So, if you look at a very long time interval t, what would be the cumulative reward that you would get? The first time a renewal occurs, we will get a reward R1. Again one more time R2, R3. So we have to add R1, R2, R3 and so on over all the renewals that happen within the duration 0 to t. N of t denotes the number of renewals that happen in a duration t. So sigma n varying from 1 to n of t or n is the total reward obtained till time t. So R of t represents the total renewal earned till time t. We will assume, because R1, R2 are all IID random variables having the same distribution, we can of course find the expected value of R or n for any general n. They are all IID, so they will have the same expected value. So we will call that E of Rn to be the value E of R. Similarly, we told that the duration of the renewal cycle, that is the time between two renewals x1, x2, x3 are all again IID with the same distribution, and it will have an expected value. So E of xn is E of x. Now let us assume for dealing with the realistic process wherein E of r is less than infinity and E of x is less than infinity. That is, the renewal cycle duration is finite and the reward that we get is also finite, expected reward is finite. Then the basic renewal reward theorem tells that with probability 1, in the limit t tends to infinity, R of t by t is equal to E of r by E of x. First of all, what is R of t? Is the cumulative reward that we have got till time t. If we divide it by t, it will give you the rate at which we get reward. And to make this average a meaningful one or correct, we take the averaging duration t to tend to infinity. So what this tells is the rate at which rewards are obtained can be found out by two ways. One, you take a long duration t, find the cumulative reward, divide that cumulative reward by t, and in the limit t tends to infinity you will get the reward rate. The other way is, if you know E of r, expected value of reward and expected duration of a renewal cycle, E of r by E of x itself will give you the reward rate, because E of x is the average duration of a renewal cycle. At the end of the renewal cycle you get reward whose average value of E of r. So if you divide the expected reward in a renewal cycle divided by the expected duration of the renewal cycle, you will get the renewal rate. That is what this theorem tells. A related statement is, in the limit t tends to infinity, E of r of t by t is also equal to E of r by E of x. Okay. This is very related. To prove this statement, we go as follows. Look at E of r, r of t by t. What is r of t? Sigma n from 1 to n of t r of n by t. So what we will do is, we will divide and multiply this by the term n of t. So sigma n 1 to n of t r of n by n of t into n of t by t. We will split it into two terms and then take the limit t tending to infinity. So by the strong law of large numbers, we find that sigma n 1 to n of t r of n by n of t is equal to E of r. What it tells is, R1, R2, R3 are all samples of the random variable r, and we are doing an average of large number of samples, okay, ensemble average, and when the number of samples taken is large, then this average will become equal to the expected value of R. Then again, if you look at in the limit t tends to infinity, n of t by t. N of t is the number of renewals that takes place, t is the duration. What is this? You look at the inverse of it. What is t by n of t? T is a long duration and n of t is the number of renewals that takes place in that. So t by n of t is the average duration of a renewal sequence. So many renewals have occurred in this duration. If we divide n of t by t, you will get the expected duration between two renewals, that is the expected duration of renewal cycles. So if you take n of t here, by 1 over t by n of t can be written as 1 over e of x, okay, as t tends to infinity. So this is 1 over e of x, this is e of r. So you get this quantity r of t by t is equal to e of r by e of x. So this is the basic of the renewal reward process. Let us look at a number of examples. The first example is from the domain of wireless networking. There is a popular medium access layer protocol called as the carrier sense multiple access with collision detection, which is usually abbreviated as CSMA/CD. What happens here is that you have a wireless network with a very large number of nodes. All these nodes are contending for the medium or the channel. Only one transmission is possible in this channel. If there is more than one transmission, we say there is a collision. The signals overlap and therefore a receiver will not be able to receive any useful information. So the idea is to such that at any given time, for the channel to be used properly, only one transmission should prevail. But at the same time, there are so many nodes which are trying to contend for this channel, and there is no coordination. No one tells that which node should transmit at what time and so on. So they will all try at a random time. Collisions will happen. So they have to detect that collision, stop, and do it in a manner that success eventually happens. That is, only one transmission happens. To do that, these nodes are usually provided with channel sensing capability. That is what as the channel sense S in CSMA comes into picture. A node can sense the channel and find out whether the channel is idle or busy. That is, some transmission is going on. When the transmission is going on, there is no point in the node starting a new transmission, because it is going to be a collision for this node, and it will not only do anything useful for it, it will also spoil others' ongoing transmission. So every node can sense the channel, and if the channel is busy, it will not attempt any transmission. It will attempt a transmission only when the channel is idle. So that solves a lot of problem. But even in this case, it may so happen that different nodes which are waiting for the channel to become idle may start the transmission at the same time, leading to a collision. If that collision happens, then again there is no point. The channel is not used properly, and it will waste the resources, the channel resources. So whenever a collision happens, we have to detect it and immediately stop the transmission so that time is not wasted. That is where the collision detection part comes. So what we do is we divide to make this practically working, this protocol, we divide the time virtually into slots, but we will call these as mini slots. In each mini slot, okay, is the time it takes for any node to sense and figure out whether that mini slot is an idle one or a busy one, in the sense whether a channel is transmitting something or not. So the mini slot is of such a duration that it will just be equal to the sensing duration of a node. So then all nodes are synchronized, in the sense that all nodes know when a mini slot starts, when it ends, and there is an coordination that nodes will attempt a new transmission only when a mini slot begins. Okay, and to avoid collision, what we will do is each node will not transmit as soon as it finds a mini slot, then guaranteed collision will be there. So we introduce a retransmission probability, call it as P, so that whenever a mini slot is idle as sensed by a node, at the end of the mini slot, which is the beginning of the next mini slot, each node will attempt a transmission with a probability P and defer transmission with a probability 1 minus P. So which means that if there are 10 nodes, 3 node may transmit, or 1 node may transmit, or none may transmit, or 5 node may transmit, and so on. Different things can happen. So what will lead to success? If there is only one node that attempts a transmission, then it will become successful. Why? When it attempts a transmission, channel will become busy. Then every node, while sensing the channel, will find it is busy and therefore will keep quiet, will not transmit. And this transmission will go smoothly until it gets completed. As soon as it gets completed, it will stop the transmission. Then there will be one mini slot where all nodes will find the channel as again become idle, and then at the end of that mini slot they will attempt a transmission. So this is how successful transmission comes. On the other hand, when two nodes or more than two nodes attempt transmission, then each node can find out whether there is a collision or not. For example, by comparing what it has transmitted with what it senses from the channel. So that is the collision detection capability of a node. As soon as it detects collision, it will stop transmission within that mini slot where it has started the transmission itself. So when there is a collision, it will take one mini slot to stop the transmission, and then it has to be followed by one mini slot which is idle for the next attempt to happen. So because of this one, if the following things can happen: if no node transmit in that slot, the slot becomes idle, and all nodes sense that the idle slot and make an attempt in the beginning of the next slot with a transmission probability P. If two or no more transmit, a collision occurs. Nodes involved in the collision detect collision and stop the transmission at the end of the mini slot. This collided mini slot has to be followed by an idle mini slot for the next attempt to happen. Then if only one node transmits, exactly one node transmits, then all other nodes will keep quiet and this transmission will become successful. After that transmission ends, there has to be an idle mini slot, after which another attempt can occur. To make this work, we have to let that the transmission duration has to be integral multiple of number of mini slots, so that nodes will remain synchronized. Further, we will assume that the length of the mini slots is sigma. Then the duration of the packet that is transmitted can be a random variable, but it is denoted as L in units of sigma. So some L mini slot it takes for one packet to get transmitted, that L is again a random variable. So this is the model for the carrier sense multiple access for collision detection. To derive the performance of CSMA CD, we have to concentrate on one performance metric called as the throughput. Throughput is defined as the expected number of packets successfully transmitted per unit time. because all attempts may not be successful. So we have to find in every unit time how many packets are being successfully transmitted. So that is the throughput. How do we find it? To do that, we will model CFSMA-CD as a renewal reward process. So we have to identify points at which the process renews itself, wherein we don't need to remember the history and so on. Suppose there is an ongoing transmission. At that time, we need to remember the history to know at a future time what will happen, whether there will be an idle mini slot, or there will be a collision, or there will be a successful transmission. The reason behind that is, at an arbitrary time, there may be an ongoing transmission. We do not know how much, when it will end, because the transmission duration is L, which is a general, follows a general distribution. It is not an exponentially distributed random variable. Here, if you assume L to be has a geometric distribution, then probably we can tell that every time, okay, mini slot history is not required. If L has a general distribution, then history is important. But when transmissions are attempted, that is at the end of a mini slot, then history can't be forgotten, because when a transmission is attempted by all nodes, then it is purely the probability prescription which will tell how the future will evolve. Each node will transmit with a probability P. There will be n nodes. Then you can find out what is the probability that one node transmits, two node transmit, and so on. For example, P is the probability of transmission. We can say NC1 P power 1 minus P power n minus 1 is the probability with which just one node transmits. That will lead to success. Or no node transmit is NC0, okay, P power 0, 1 minus P power n, and so on. That way we can find out on 1 minus probability of 0, 1 minus probability of 0 or 1 node transmits is the probability of 2 or more node transmits. Everything can be figured out. And the expected duration E of R, E of L can be used to predict the future evolutions and so on. So we will model it as a renewal reward process. We can say that the end of every idle mini slots node can attempt transmission, and these are the renewal points. First thing we have to do is to find the duration of a renewal cycle. The duration is random again. That depends upon what happens in the renewal cycle. If the renewal cycle happens to be an idle mini slot, because if no node transmit, then the next attempt can occur in the beginning of the next mini slot. So the renewal cycle is just one mini slot of duration sigma. So it is just sigma if no node transmits. That is the ideal case. Or if two or more node transmits, it will take 2 mini slots for another chance for another attempt. One mini slot of duration sigma to detect collision and then stop the transmission. One more mini slot of duration sigma to let the channel become idle for node to make any attempt at the end of it. So in case of collision, it will be 2 sigma. In case of a success, it will be E of L plus sigma, because E of L is the expected number of mini slot it takes for a transmission to get over, plus 1 mini slot to make the channel idle for the next attempt to begin. So what is the expected duration of renewal cycle? These are the 3 possible events. Each one has got its own probability. We have to weigh it by their probability to get the expected duration of the renewal cycle. To that, we will introduce this notion. PS, PC be the probability of successful transmission and a collision to take place respectively. In turn, using the nature by analyzing the wireless network, these probabilities can be arrived at. We will not get into that one. For example, in the case of the wireless LAN, classical wireless LAN called as the IEEE 802.11 DCF, we have a Bianchi's Markov chain model which can be used to derive the transmission probabilities, which in turn can be used to find the success and collision, which I have already mentioned. Success means just one transmission where tau is the transmission probability of each node. Similarly, collision can also be found out. So, from this information we can find the expected duration of a renewal cycle. It is just sigma if no node transmits, which is 1 minus PS minus PC. Is P idle? 1 minus success probability and collision probability. Sorry, this should also be minus. 1 minus PS minus PC. And 2 sigma if there is a collision with probability of collision. And EFL plus sigma probability of success. So, you have found out the probability of the expected duration of the renewal cycle. Now, reward. What is the reward? We already defined throughput is the expected number of packets transmitted per unit. After all, it is the packet transmission that we are interested in. We want to transmit as many packets as possible successfully. That is the reward. So, in one cycle, renewal cycle, what is the expected number of packets that will be transmitted? Well, so 3 things can happen. When the slot becomes idle, no transmission happens. When a slot becomes a collision one, okay, when an atom becomes a collision one, no successful transmission occurs. Although there may be transmission attempts by more than one node, they are not successful. Again, it is 0. Only when one node transmits a successful transmission attempts. So, the expected number of transmission, successful transmission, is just 1 into probability of success plus 0 into probability of idle plus 0 into probability of collision, which we will ignore it. So, we will just write it as 1 into PS. So, expected reward E of R is PS, then E of X, the expected duration of the renewal cycle, is given this one. So, S, the reward rate, which is the throughput, capital S, is PS divided by this numerator. This is how we can use the renewal reward concept to derive the throughput of a wireless network. Then we will look at a more common sense model, a car buying model. Okay. Suppose let us assume that the lifetime of a car is a uniform random variable between 5 to 15 years. Let us assume that when a car is bought, a 5-year warranty is given. Car may break down, but it is up to the manufacturer to repair it and give it. So, it is okay to assume that it is uniformly distributed between 5 to 15 years. The owner has a policy that he buys a new car as soon as the old car breaks down or reaches an age of 10 years. Okay. If a car breaks down, by that we normally mean a major one, not a minor one wherein we simply repair it and use it. A major breakdown is what we are really talking about. Then he decides to discard it and buy a new car. Otherwise, when the age becomes 10, he becomes very worried that anytime it may break down. So, even though there is a likelihood that it can work till 15 years, he will again discard it once 10 years is over and then buy a new car. Suppose let us assume that the car is being bought using a scheme called as the exchange program, wherein you give a car in a working condition, then a new car can be bought at the rate of 5,000 units of money. Okay. For that you have to give a car, however old it may be, but in a working condition. Okay. So, the car should be in working condition when it is exchanged. Assume that it takes 800 units of money to repair a car when it breaks down. Okay. So, what will be the long run average cost incurred by the owner? So let us look at the pros and cons. See, normally you would like to use the car. See, if you keep buying the car very in a repeated manner, you will end up paying more. You would like to use it as much as possible. Okay, so that tells you that you have to keep using it till 15 years. But there is a catch. See, when a car breaks down, you have to make it into a working mode before exchanging it. To repair it, it will cost 800, and then to buy a new car through the exchange mode is 5,000. So you will end up paying 5,800. On the other hand, at the end of the 10 year, if you decide to give it off, it will only cost you 5,000 units because the car is working when you decide to give it off at the end of 10 year. That is why it is not a good method, to a greedy method where you continue to use till 15 years and then give it. It's after 13-14 years is very likely that it will break down, you will incur a 5,800. But at the same time, at the end of 6th or 7th year, it is not a good idea to give it because it is likely that it may not break down so quickly. So there is an optimal sweet spot or an optimal time. We can indeed derive it, but we will not do it at this one. We will take it to be 10. So what is the long run average cost of the owner? That is the ownership cost per year of the owner if this policy is being used. Again, at an arbitrary time, if we ask, okay, what will be the ownership cost for the next year? Again, that depends because about the age of the car at that time and so on. So history cannot be forgotten. But when a new car is being bought, then history can be forgotten. You don't need to know about the previous one. A new car, if it is bought, you know that what is the cost you have incurred, and you also know the lifetime distribution, you know the cost of a new car, you know the cost of a repair, and everything is known. So history can be forgotten. So those are the renewal points. Okay. So once we understand this, what is the reward? Here reward is the cost. What is the amount one has to shell out in order to buy a new car at the end of a renewal? Because renewal cycles are the one we have a new car, which means that you should have bought it, so some money has to be incurred. So what is that? Okay. So then the rate at which you spend money year after year is the expected cost incurred during a renewal cycle divided by the length of the renewal cycle. E of R by E of X is the is the reward rate. Here cost incurred, ownership cost. Let X be the lifetime of the car during some arbitrary cycle. Okay. Then the cost incurred in that cycle can be found out as follows. Suppose X, the time till the lifetime means the time till the breakdown of the car. If X is less than or equal to 10, it means that before giving up the car, it breaks down. In which case, you have to repair it and then go in for an exchange program. So it is 800 plus 5,000. So it is 5,800. This will happen whenever X is less than or equal to 10. But when the lifetime exceeds 10, then what we do? At the end of the 10 years, we exchange the car for 5,000. See, note that we are not waiting for the car to break down. Okay, whenever the car works till 10 years, that is when X, it means that lifetime is sometime later than 10 years. Under this condition, it is 5,000. So what is the expected cost during a renewal cycle? Is the expectation of this one. So it is 5,000 into the probability that X is greater than 10 plus 5,800 into probability that X is less than or equal to 10. Now, what is X? X is a uniformly distributed random variable between 5 and 15. Then what is the probability that X is greater than 10? Okay, you can see that it is equal to 1 by 2. Okay, that is 1 by 2. And what is the probability that x is less than or equal to 10? Okay. So you can see that the mean of this is 15 minus 5 divided by 10. Okay. That is yeah, by 2 actually. Okay, that is 1, that is 5, the mean is from the 5. Okay, 15 minus 5 divided by 2, which is 5, 5 plus 5, it is 10. Okay. So probability that x is less than or equal to 10 can be found out. You can see that it is uniform between this 5 and 10. So the expected value will be 5 plus x by the 15 minus 5. That x is 5 was what we have to put in order to find the CCDF at 10. Okay, 5 plus 5 divided by 15 minus 10, that is how we have to put. So you get 1 by 2 is the probability. Okay, not the probability will be this is also 1 by 2, that is what it will come down to be. So from that you can find out that it is 5400. So what is the length of the cycle? Okay, that is again a random variable. So length will be x, the time at which failure happens. If failure happens before 10 years, and it is just 10 when the life cycle exceeds 10. So you can find the expected duration of the length. So it is 0 to 10 x into fx of x dx plus 10 when x exceeds 10. This can be found out by integrating from 10 to infinity 10 into fx of x dx. So here if you look at this, fx is 0 from 0 to 5. So the integral you will only have to start from 5. 5 to 10 x into 1 by 10, because fx of x is 1 over 10 between 5 to 15 into dx, that is the first term. The second is 10 to, again it's not infinity, 15, 10 into 1 by 10, this one. So you can, here it is 1 over 10 into x squared by 2, substitute, okay, 10 squared minus 5 squared and so on, you will get this value. Here again it is just 1 into 15 minus 10, it is 5. So you get it as 8.75. So you have to find the expected long run cost is 5400 divided by 8.75, which is 617 units per year. Okay. The next example is related to car or a train depot, okay, and wherein the customers arrive to that train depot in accordance to a renewal process with a mean inter-arrival time as mu. There is a policy that for every customer you cannot dispatch a train, because a train has a number of seats, totally n seats, and therefore n customers can be accommodated in a train. So only when n customers are accumulated in the depot, a train is dispatched. Let us assume that a number of trains are there in the depot waiting for to take customers as soon as n customers accumulate and so on. But these customers have to be accommodated in the station, and therefore it incurs some cost for the one who runs this train service. And the cost of expenditure for accommodating the customer depends upon the number of customers. It is, let us assume that it is n units per customer, and if there are C per customer. So when there are n customers, then the rate is NC is the amount you will spend, is the rate at which you will be spending when there are n customers in the depot at the rate of C rupees or dollars per customer. So NC is the rate at which you will be spending on the customer to entertain the customer while they are waiting for the train to leave. So here is the trade-off. If you keep n to be large, it is good because you are running one train service. But in accumulating large number of customers, you are spending on the customers' upkeeping. So that is again a cost. Right now we are not looking at all those costing details in fully. Okay, we can model all those things. We will just look at the rate at which expenditures are made by this depot. Okay. Again we will assume that because the arrival process is a generic process with a mean inter-arrival time as mu, then history is needed at any time to predict the futures. But at the time train leaves, history can't be forgotten, because as soon as n customers come to the department, immediately a train leaves, which means that as soon as the train leaves, there will be the depot will be empty. So we know many things. One, a train has left and the depot is empty. Then how customers will arrive, we will know. It's a generic process with a rate of mu, mean inter-arrival time is mu. So we have to wait for n such customers to arrive, and every time we can know the count of the customer and also know the rate at which you have to be spending on the customers. Everything can be found out. So the time at which train leaves are the renewal points, and the reward is again the cost that you incur on the customers by spending on them. You can also include other costs, like you will be getting some money which the customers will be paying for as the train ticket. So if the ticket cost is T per customer, and if a train leaves, n into T will be the profit the company will be accumulating. That can also be modeled. We are not doing this one, but the scope for making the model more realistic is there. So what is the cost of spent on a cycle? It is the expected cost, okay, during the renewal cycle. See, till the point as soon as one customer arrives, till the point the second customer arrives, which means that when there is one customer, the rate of expenditure is C. When there are two customers, it is 2C. When there are three customers, it is 3C. T1 is the time it takes for the first and second, between the first and second customer. T2 between the second and third. So it is C times T1 plus 2C times T2, 3C times T3, and n minus 1 C times Tn minus 1. This is the total amount of money the depot is spending on keeping the customer. These are all expenditures. The return, as I mentioned, can be n into T. So the total monetary benefit is Nt minus this, if you are including modeling that. We know that E of Tn is mu. So if you take the expectation over it, it will be C times E of T1 plus 2C times E of T2 and so on. E of T1, E of T2 are all mu. So we can take it as C mu into 1 plus 2 plus and so on n minus 1. So it is C mu into n minus 1 by 2. That is the total cost that is being spent. What is the length of the cycle? How long it will take for n customer to arrive? It is actually n into mu. So the expected reward divided by the expected duration of the renewal cycle is this one. So on cancelling n and mu here, we will get C into n minus 1 by 2. So this is the way the renewal reward process can be applied to deal with, to model dispatching of a trip. So we will stop at this point. We will look at the regenerative process in the next lecture. Thank you.